Hello. In this video, I'm going to talk about the hybrid neurosymbolic architectures on the path to interpretable, strong general artificial intelligence. So I would like to start with the short video, and this video has been created by my colleagues in Novosibirsk, and this video shows how the reinforcement learning problem can be solved by means of what is called probabilistic semantic modeling, implemented by discovery system designed by Professor Evgeny Vityaev and his colleague from Novosibirsk. On this example, we can see that the mice learn to find the cheese. And they learn to find the cheese by means of having the outer world, including the surface, including the ability to turn left and right and to move forward when after they turned, and ability to see the goal and the ability to reach the goal and take the goal. Everything of that is encoded in terms of predicates which correspond to particular features of the surrounding reality. So the set of predicates describing this reality builds kind of small world ontology, and these mice are capable to learn to operate within this small world ontology, reaching their goals. And on the right side of the screen here, you can see the flow of actions and the predicates being perceived and acted by these mice. And what is also important here, and these mice are able to learn cooperatively using the statements in this language that you can see on the right. That means the experiment shows that if each mice learns on its own and keeps its own model of the world and ability in order to predict the outcome of their actions, then they learn relatively slowly. But if they can broadcast their experiences, sending the knowledge about the world to every mice on the same environment, so they can acquire the knowledge from each other by means of so-called transfer learning, which is happening by terms of such a language and in terms of such a language, and then they can learn to collect more cheese and collect that cheese faster, much faster than they would be trying to do that alone. So then let's focus on current AI and AGI frontiers. And AI is artificial intelligence, AGI is obviously artificial general intelligence. So there are a list of directions of further improvements for this technology, but I would focus only on top 3 of them. And the first one is a modern trend to somehow integrate neuromorphic or subsymbolic technologies like neural nets and symbolic technologies like ontologies or inference engines together to build integrated cognitive architectures, taking the best of the two worlds, including neuromorphic or subsymbolic world and symbolic or reasonable or inference engine world. And these integrations are expectedly helping to solve the two practical problems. And the first practical problem is building explainable and interpretable artificial intelligence, where explainable means that people should be able to have the decisions made by artificial intelligence explained, so they understand the reasons why particular decisions are made, and such a requirement is actually required by law in some countries. For example, take algorithmic transparency requirement and regulation by European Union. But also it means that the models on themselves would better be interpretable. So even before a specific decision is made, people would be able to perform the audit or inspection of the knowledge of the artificial intelligence system, which is critically important for security and security domains and particular areas which are very sensitive to mistakes and may be lacking enough training data, so the knowledge may be taken into the systems in terms of rules. Like consider military applications, defense applications, nuclear power, control and protection. So in all of these cases, you can't afford too much try and fail, and reinforcement learning based on mistakes and error propagation. So you can teach system for nuclear power plant protection and or for defense applications protections. Such systems can be trained by the error propagation, because you can't afford to have too much data with errors, so you can propagate these errors, right? And another aspect of why neurosymbolic integration systems may be practical is because of the transfer learning, where we would like to see the artificial intelligence systems to perform most substantially like humans perform. Like any human can not only explain what they learn, but any human can also integrate or accept or consume the knowledge explained by other human. So I can explain my knowledge to you, and you can acquire my knowledge and use it in your own life, and you don't need to have a lot of training to consume some instructions that are provided to you verbally or written in the book. Like for example, you may be given instructions to operate the car or operate some vehicle or some device, and you don't need to do it by trial and fail. You can just follow the instructions that you have acquired by means of the transfer learning. If we speak about the symbolic, subsymbolic, or neurosymbolic applications or integrations, we can consider two different approaches. One approach is kind of horizontal neurosymbolic integration, where on one hand, on the right here, you see the neural network with some distributed representation of the knowledge in terms of weights of the neuron to neuron connections across the layers. And on the other hand, you see the logical network made of predicates, and the predicates may be connected by Boolean logic operations, or they may be connected by some fuzzy logic or probabilistic logic operations. So these arrows may be weighted or not weighted. That's a separate question. What is important here is that every node and every link on such a network on the left has some specific semantic meaning and can be interpreted by a human or inspector or a user. And given these two representations, we have a bunch of options. First of all, we may have to come up with the idea of how to extract the distributed knowledge of the neural network and represent it in the reasonable model of the logical graph or semantic graph. And so then you explain the model. And then, given you have the knowledge already present in form of the graph, you can transfer this knowledge back to the neural network, or you can transfer it to another neural network. So you solve the problem of explainability and transferability of the knowledge at once. And if you want, theoretically, once you have the knowledge explained or extracted from the neural network, you can keep your inference engine working with this knowledge in the semantic representation on the left, or you can create it in semantic representation and then upload it back to the neural network or to the fresh neural network, and then let keep it operating in the neural network. It all depends based on the application. What's important here is that once you have the knowledge explained, you can make sure that the logic of the knowledge that you have in distributed representation on the right doesn't have any side effects or artifacts or other subjects of adversarial attacks. Like for example, you may find that if you extract the model of the horse from the distributed representation on the right to semantic representation on the left, you may find that besides ability to have hooves and tail and being white and black or brown, you may find that the horse should have a green background, which would be true. That kind of attribute or feature would be false just because of you have had a lot of horses on the green grass in your training set, and so you just can take this green grass predicate in the logical structure extracted from the neural network, and then you can remove this false attribute. So and after that, when you use the semantic representation of the knowledge or upload this corrected semantic representation back in the neural network, you will be able to recognize horses even on the paved road, or in some, or maybe just bathing in the sea where there is no grass. Another example of the neurosymbolic integration or hybrid neurosymbolic cognitive architecture is what I would call vertical neurosymbolic integration, and this idea is inspired by design by Marvin Minsky on one hand, where he describes the hierarchy of agents responsible for higher level of abstraction and operation and perception, and lower level agents responsible for lower level of operations and perceptions. And given this hierarchy of agents, you can assume that there may be higher level agents which operate in terms of the concepts and relationships and objects and properties and particular scenes and scenarios involving them, like the horse is eating grass or the man is running into the store and so forth. And on the lower level, at the bottom of this scheme, you see distributed representations of the features of this man and horses in different circumstances, and at the bottom you do with distributed representations which doesn't need reasoning. And given such a vertical hierarchical representation of the scope of the knowledge, you can terms of it in terms of ideas provided by Daniel Kahneman about two different modes of thinking: ability to think fast and think slow. So the idea here is that if you operate at the higher level of abstractions in terms of scenarios, objects, and features, it's easy to learn. Because if you are given instructions like take this book and put it on the desk, or put the key into the key slot in the car and turn it right till the engine starts, and then press the brakes and release the brakes and press the gas pedal, and the car will start moving, you can hear this instruction just once or two times in your life, and then you are able to start the car. But when you start the car first time, you need to do it slowly. So this level, upper level of perception and action, means easy explanation. So you can deal with instructions, learning fast. So once you heard the instruction one or two times, you can already execute these instructions. But you need to think slow. You need to drive carefully when you drive the first time, right? On the other hand, when you have repeated the same procedure multiple times, it can be implemented at the bottom layer of perception and action, and that's another thinking mode. That's about thinking fast. So when you operate at the distributed and subconscious and subsymbolic level, so it's subsymbolic because it's symbolic on the top and subsymbolic on the bottom, obviously, right? So when you think at this subsymbolic level, you think fast. But in order to be able to think fast, you need to learn hard. So in order to think fast about something, about to perform subconsciously and quickly response to some unforeseen circumstances, you need to have a lot of training for this particular skill. And you are not always able to explain what you have learned in such experiential way based on multiple exposures to the training set data. So this way or another, whether we are thinking fast and slow, or slow and learning fast and slow, let's take a step back and consider some universal cognitive architecture which can be used to take together these two different modes of thinking, symbolic and subsymbolic. So here is the design that I have created based on ideas of Evgeny Vityaev, and Evgeny Vityaev is deriving his work from ideas of theory of functional systems, or TFS, suggested by Petr Anokhin. And this version of the design assumes that there are 4 kinds of the information that should be stored within the agent memory, and 3 different kinds of activities that have to be performed by the agent. And by the way, this scheme is just functional, so the implementation may be different. For example, in human brain, there is no separate operating modules like compressor, predictor, and decider here, and there is no any special storage to store the graphs or the data, semantic data, or distributed data, distributed representation. So in the human brain, or the same neurons are used as a structures to store the information and the processors to handle this information. That's quite smart and interesting design. In the computer architectures, we may have a different. So we may have a database, and we may have some code that deal with this database, or we can somehow mimic the activity of the human brain. So here I am just separating things to make the functional discussion about what we need to deal with. So if we consider the data that we store, we need to store the actions that we direct towards the outer world, and that's directed action log. Then we need to retain the evidence that we observe, and then we need to keep the models that describe the possible rules and policies and causal model, and keep the causal models of the events in the outer world and the possible responses to the actions that we direct towards this world. And finally, there are some base values that may be hard-coded, or they may be given to us, and the goal of the agent is to have all these goals all reached, or have its all base values satisfied and kept in a state where all values are kept true or kept reached. And then, given this knowledge, we have 3 kinds of activities. First of all, there is a predictor, and the purpose of the predictor is to take the observed evidence and infer the models of the world, so it can make prediction of what is going to happen next when something is happening right now. Then there is a decider, which considers all possible predictions based on all possible actions that the agent can make given the observed evidence and predicted models, and the decider makes decisions based on the base values. And the order or idea of the decider is that it can take only these scenarios predicted by the predictor, where these scenarios are capable to maximize the ability to reach and satisfy the base values hard-coded or acquired by the agent. And then the decider selects the scenario that is satisfying the agent's needs to the greatest extent, and it directs the action, which is recorded in the direction action log. And finally, there is a processor component, and the processor component needs just to keep agent to stay within the limited amount of resources available to keep these models, because if agent would retain or keep their everything about the happenings, all happenings in all events, all actions, all possible situations, all possible states of the environment, and its own mind in its memory, the memory will be overflown. So, and it will be never able to make predictions because of the combinatorial burst of all possible known states and histories of its life. So the goal of the compressor is to build abstractions, remove the junk, collect and throw the garbage, and keep only those models and only those possible scenarios based on these models that might be useful for making predictions and making decisions in most of the cases in agent's life. And if some cases are rare or not relevant, or there is no impact on the ability to reach base values based on the following or not following these scenarios, this kind of these parts of the models can be forgotten or kept in garbage. And here is example how we can use this architecture in order to solve some simple task. So here is the Atari breakdown game simulation, where the goal of the agent is either keep the rocket in place, or move the rocket left, or move the rocket right. And the idea of the rocket is just catch the ball, so the ball is not hitting the floor of the game board. So whenever the agent is capable to get the rocket to so it catches the ball, and the ball is not hitting the wall, then the agent is getting happy. And if the ball is hitting the floor, because of the agent is not able to move the rocket in the right direction, then the agent is sad. And the hard-coded base value of the agent is always be happy and never be sad. And on the right we can see, and here we can see the list of 5 functions which can be represented as predicates of the position of the describing the position of the rocket and the ball, and the perception of being either sad or happy based on the situation on the game board. So using just all these 5 functions and having the values of these functions being streamed into the agent's perception channel, evidence log, and generated by the and having the left and right movements generated by agent in the action log, we can see development of the agent's experience to handle this problem. Here you see that initially agent tries to make some random movements, and most of the random movements are not making it possible for agent to catch the rocket, and then every time when the to catch the ball, and whenever ball is hitting the floor, the agent is getting red feedback. So the red feedback, the red line on the charts on the right side, means that agent is missing and agent is sad. But whenever agent makes the right move and the ball is hitting the rocket rather than floor, the agent is getting positive feedback. The agent is given a blue line, which means the agent is happy. And we see that over the time agent is getting more and more happy, and in the last third of the session the agent is always catching the ball, and agent is always happy. The more you can see the code and the design of this kind of cognitive architecture, and the code implementing this at the bottom of the screen. And here's the more complex design of such a kind of agent potentially capable to solve this problem, provided by the work of Evgeny Vityaev and his colleagues, based on the theory of functional systems suggested by Piotr Anokhin. And also the theory of functional systems derived by Evgeny Vityaev and his colleagues can be also used to build true mathematical model of the single neuron, which appears much more complex than the reduced neuron model used in the neural networks, because any neural network design doesn't account, any artificial neural network design accounts for multiple branches of the dendrites, and it is known by the latest publications in Nature journal that this branching on the dendrites also contributing to the information processing by individual neurons, and that a true mathematical model of the single neuron is much more complex than just a node and multiple links pointing to the other nodes. And given this true mathematical model of the single neuron, and using the theory of functional systems framework, the agent can be learned to perform some activities that are found in the nature. For example, here we see the mathematical model of the C. elegans nematode, which has a neural network system made of a few hundred neurons. And you can start with just every neuron knowing nothing, and we put this worm into the situation when there is a chemical gradient, and the goal and the positive field of the agent is assumed to increase the chemical gradient along the moving in the space. And the agent and not an agent, actually the society of minds, where every mind is a single neuron of these few hundred neurons. So each neuron of the neurons performs individually, getting feedback from the environment and from the other neurons. And then eventually, when the neurons are trying to act cooperatively, trying to maximize feedback for every individual neuron, then eventually we can see that motions of the worm, artificial model of the worm, are getting more and more natural, and eventually we can see that the worm is capable to actually start crawling towards the increase of the chemical gradient, showing the patterns that are actually corresponding to the patterns of the motion of such real worm in the nature. So given this simple model describing particular kind of perception or action, we can build more complex cognitive architectures where every block potentially can be either based on the neural networks, or it can be based on the inference engines operating with symbols and probabilistic or fuzzy logic, or it can be some symbolic or subsymbolic integration system with vertical neurosymbolic integration or horizontal neurosymbolic integration. What's important here is that every level in this tower is getting inputs from the outer world and getting feedback from the outer world. And the outer world for every layer of such cognitive architecture, or for every brick in this tower, is provided by the inputs of the sensors or other neurons outside. Like, for example, if we are reading the strokes of the characters or glyphs on the screen, we are getting inputs from the sensory cells, and we are getting feedback from the neurons responsible for reading letters. And if the feedback for reading letters is right, then we assume that that the settings of the neural network or cognitive system reading strokes is correct, because it's working correctly, because it recognizes the letters. Then further, when we have the letters recognized, the module which is recognizing the letters from the strokes is getting feedback from the module responsible for reading words. So assuming that the letters are assembled by the into the words correctly, we are getting the feedback from the other module responsible for reading words. And moving forward, we can actually reach the level of the comprehension of the entire sentences, and then we have the level of the meanings. And if we see some text in Chinese, and if we expect this text to be actually representing some set of the Chinese characters, conveying some words in Chinese, and some sentences having some meaning in Chinese, we are getting the feedback propagated from the our central high abstraction level of meanings down to the every layer which is responsible for more fine-grained operations. And the same hierarchy of blocks or bricks can be considered when we perform the action towards the outer world. And this kind of basic architecture of multiple segments of the cortex, or multiple agents of society of mind suggested by Marvin Minsky, or any individual agent or submodule of this system, can be this architecture can be applied for multimodal perception and multimodal action. So we can apply the same architecture to read, to recognize objects, to read letters, to hear some sounds, pitches, and spoken words, to write, to read, to draw, to any kinds of activity. And what is important here is that such a multimodal perception makes it possible for what is called mutual grounding or multimodal grounding, when at every layer of such perception you have feedback not only from the bottom layers or from upper layers based on the level of abstraction, but also from the lateral perception channels corresponding to different modalities, like seeing something may be supported by hearing something, and feeling something may be supported by reading something or listening to something. All that said, here is what I am doing is my own project. So I'm working on personal artificial intelligence, and that is can be used to build personal agents for social and media intelligence applications for business. And what we do this kind of multimodal perception, aggregating valuable information from different media sources, like from news sites, RSS feeds, any websites, Google searches, social media channels like Telegram and Reddit, social networks like Vkontakte and Facebook, messengers like Telegram and Slack, and we can aggregate all this information in a way usable and practical for the users of our system. And we use the Aigents deep pattern technology for language model for text processing, and this model is actually making it possible to provide interpretable and explainable solutions for the information extraction, text summarization, and text classification and text relevance assessment. So thank you for attention, and goodbye.